Fischer here from the DeSo Foundation with Piotr to go over our latest feature rolling out on the DeSo blockchain called Hypersync. So before we get started on that, I would kind of like to introduce Piotr a little bit and his credentials and how he joined the DeSo team. So Piotr, do you want to tell a little bit about your background?
Yeah, sure. So hey, everyone. This is a new format for me, so I'll try to do my best. I hope that you guys will like this video and find it informative and you'll learn something. So my name is Piotr Nojszewski. I'm one of the core engineers of the DeSo blockchain. I've been developing the DeSo core for a few months, shy of a year now, and had the opportunity to work on a couple of exciting changes, such as derived keys, group messages, and recently Hypersync, which is the topic of today's video. And also, I'm still in college, so as you can probably tell by my face, I'm pretty young. I'm a senior undergrad majoring in computer science at Boston University, and my main academic interests are blockchains, cryptography, distributed systems, mathematics, all the good stuff. Ooh.
Oh yeah. So Piotr, you've been one of the most impressive people I've met since joining DeSo.
Oh, thank you.
So one thing that I thought that stuck out when I first met you was how long have you been programming for, and what do both your parents do?
So I might be a little bit biased because both of my parents are actually like educated computer scientists. My dad actually has a PhD in computer science, like back in the old days where like they did like, so he had a PhD in artificial intelligence. So back in the days, they didn't like do neural networks. They did like expert systems. So it was just all decisional systems. So, you know, back computer science. But I started coding, I guess, like through like the influence of my parents, I guess when I was like 10, 12, maybe earlier. I don't know. The first thing I did was like game maker. So like making games was obviously the first direction. You play games and you make them. So yeah, and then just kind of like learn Java and other programming languages.
And then just kept scaling up from there.
Oh,
all
yeah.
Right. All righty. So let's kind of dive into the topic that we're going to talk about today, which is Hypersync. And for those who don't know what that is, it's basically a specific optimization to node syncing on the DeSo blockchain. So my first question to you would be, what is node syncing? What does that exactly mean?
Yeah, so that's a great question. And I think it begs to kind of like explain how blockchains work on a high level. You know, a lot of people consider blockchains as very complex. They think these are like the black boxes that you don't really know what's happening in there. But on a high level, it's not quite complicated. So pretty much what a blockchain is, it's a combination of a database. Okay, so you have a database, and then it's a list of transactions. And pretty much you just apply these transactions to the database, boom, you have a blockchain. But with a few twists. So transactions have to be added in a very specific way. Once you add a transaction, you cannot like remove it. You cannot delete transactions. You cannot move them around. They have to be applied in the very same order. And you bundle transactions for convenience into blocks, and they form a blockchain. So you start with the first set of transactions, the first block called the Genesis block. Then you add another block, second block, third block, fourth block, and so on. And then after a lot of blocks, you have blockchain, and you know that's kind of like where all the data lives. And there's these nodes on the network that are continuously communicating with one another, validating new transactions, adding new blocks. So syncing is a way for another node to join the blockchain network, okay? And that pretty much means that a new computer, like even your own computer, downloads a certain software and then downloads all the blocks from other nodes on the network. At least that's like the very standard approach of syncing a blockchain, which is called block sync. So so that's pretty much the high level of what node syncing is, Ty.
Yep. Couldn't have said it better myself. I feel like a lot of people, when they hear blockchain, like you said, they think it's this weird black box where there's like, just all this mysterious stuff behind it. But in reality, it's just pretty much a database with a limited set of transactions. And then basically you have a bunch of nodes talking to each other to make sure that they're decentralized and trustless. So
very important.
I guess, yes, absolutely. So my next question for you is, Hypersync is obviously trying to fix a certain kind of problem around existing node syncing problems. So before Hypersync, what was syncing a node on DeSo like? For example, how much time would it take for a node to pull in all the data prior to Hypersync?
So let me ask you, while you're listening, I can obviously tell it, but I think if we make it a little bit more interactive, it might be better for people to listen. So in the scheme that I've just outlined, which is you have all these blocks and all these transactions, okay? And when you sync, you download all the blocks, you go through each transaction one by one from Genesis up to what's called a tip, which is the most recent block. You go through all these transactions and you reprocess them. And like putting the results in the database. What do you think is the problem with this approach? Like, does anything stand out to you as like being slow or suboptimal?
Mm-hmm. You are going through all the transactions, if that question was geared towards me. I know it's going to gear towards everybody.
Yes, but you're just a listener here, like pretending that you're somewhere in the void just watching this video. But yeah, so downloading all these transactions is actually and reprocessing them is pretty slow. So block sync is doing that. But what if instead of going through all these transactions, you just download the database that is the result of these transactions, and then, you avoid a lot of interesting, weird problems, such as if you have transactions, let's say on blockchain, it's financial transactions. So let's say I send you $1,000 and then you send me back $1,000. So these two transactions moved $1,000 to you and then back to me. So money didn't really change. We still have the same amount of money, but these are two transactions that you would have had to process if you block sync. So in state sync, you just download the database, okay, that is, the state of the blockchain after all these transactions, and that is just theoretically and practically much more efficient than downloading blocks. The practical difference, one more thing is that in block sync on DeSo, it takes 8 hours, and state sync, current Hypersync takes 20 minutes. So I'd say that's quite an improvement.
Okay, yes, 100%. So you're jumping a little bit on the gun here with hopping to the awesomeness of Hypersync. But I know. But one point that I really want to drive home is prior to Hypersync, it took approximately 8 hours for a node to sync up.
Correct.
That is a time commitment that slows down development, that slows down all sorts of other things, like people have to plan around these kind of things. And this issue isn't actually unique to DeSo. We were kind of talking about this before, Piotr, but how long does it normally take for other chains roughly to download their state? So let's look at Ethereum, which I think they're shy of 300 gigabytes. I could be off here. But
makes sense.
But I did some Googling, and it seems like a lot of node operators usually say that it takes around 2 to 5 days to have their node sync up if they're using relatively decent hardware, not state of the art. Yes, very, very slow. And granted, Ethereum does have a larger amount of data to parse through than DeSo. If we had the same amount of data pre-Hypersync, I think we would probably be somewhere along the same lines of that. But basically, as these apps continue to grow, there's going to be more and more data that will need to be parsed through, which means this time will continue to grow and grow.
Mm-hmm. I don't think it would take us as long as Ethereum because they have some design choices that actually makes it slower compared to us, for example. And these design choices in particular, we try to improve on with things like Ancestral records or Elliptic Sum, which we're probably going to get to.
Yes, absolutely.
But we actually wouldn't take 2 days if we had their scale. We are probably I'd say a quarter, maybe a fifth in terms of amount of data that they have. So it could scale like linearly, so
Mhm.
it could be less.
Why did we need to have a significant improvement to our node syncing structure?
Yes, and there's two answers of it to this question, and one answer is kind of like going off of what DeSo is trying to do in the first place, and then also what are the requirements of this thing that we're trying to accomplish. So I guess it might make sense to just like go through these two responses in order. So the first thing is, at DeSo we're trying to create an engine that can power multiple social networks. So we can have like you can have Twitter on top of a blockchain, you can have an Instagram, Facebook, or maybe even a TikTok on top of a blockchain, right? And if we do that, okay, that is a difficult task to do with a single platform. To do it with multiple platforms, even more complicated. So we have to get as close as possible to what you would do on Web 2, all right, and Web 3. So one of these things is just downloading data as if you were just downloading it from like a server, So like if you download content from like YouTube, you just download the data. You don't care that there's like cryptography going on there and all that stuff. You care about speed and scalability. So one of these like software requirements is that the data that we process is not finite. So financial data is kind of like, the only thing you really care about is how much money you have, and then maybe transaction history. But the amount of money that you have is just a single number, right? Like maybe you have like different, like a checking account and then like a savings account. So maybe there's like two balances instead of one. But overall, the data requirements are pretty insignificant compared to the social use case when we want to create like a YouTube. Okay, a single video can be more than like balance of like a million people or something, because like, and moreover, when you're a creator, you keep adding content. You don't just like modify the existing content, you create new and new content. So we actually drew a distinction between these two use cases, and we call the finite state applications the one that rely on just finite amount of data. So financial systems are an example of that. And then infinite state applications, such as social applications, which require you to keep adding new data, and they just require different software solutions. So Hypersync is able to get into that infinite state niche that we're trying to operate in.
Mm-hmm. Yeah, I think that's a great way of explaining it. Basically, on DeSo, a user's data is potentially infinite. They can write unlimited posts. They can have like as many followers as they want. They have all sorts of things that basically are data heavy. Where at the end of the day, on Ethereum, if you hold 1 ETH or 10 ETH or 20 ETH, that's just a matter of writing out a number, which is basically attached to an account number. So
Exactly.
basically what Piotr was saying was there are very different ways that these two blockchains store data. Mm-hmm. So this is one of the main reasons why we, or I should say Piotr, built Hypersync. So Piotr, could you explain to me on a very high level what Hypersync is and what Hypersync does?
Yes. So remember the block sync and the state sync? Remember that? So
yep.
Hypersync is an example of state sync. Okay, there's different blockchains doing like different types of state syncs. Ethereum is doing 3 of them. They have warp sync, snap sync, fast sync. All of them do pretty much the same things. It's just like maybe one thing in like little details changed, but they're very similar. Solana is doing a state sync. So the general approach is that. So instead of downloading blocks in order to sync, you download the state. So much faster sync time. And, Hypersync is just state sync with combination of couple of in-house technology that we developed that are pretty exciting, mm-hmm. and no one really did that before. So,
and we're going to dive into some of those subparts in a bit here. But could you say again the new sync time with using Hypersync versus the old sync time?
20 minutes versus 8 hours.
Which, when I first heard those numbers, I thought was absolutely insane. And I don't know, I got so excited hearing that. That is one of those things which is just like a game changer, I feel like.
Mm-hmm.
Now node operators working on DeSo, they're not going to be like, oh, I'm just going to let my node sync and I'll come back tomorrow. It's, no, I'm going to let my node sync and I'm going to go grab a snack or something and we'll be good after that.
Yeah, literally, right? Like that's the order of magnitude faster, right? Like 20 minutes to 8 hours. How many times is that? Like 324 times faster. Like that's pretty good.
It is crazy.
Yeah.
So with Hypersync,
that's what we want to do at DeSo, you know, not just the syncing. A lot of things and get better than state of the art. So. That's the goal.
Plenty more awesome optimizations to come. And I'm sure, Piotr, you're going to be one of the guys behind a lot of those improvements.
Proof of stake next.
Proof of stake next, yep. To get into Hypersync, at least on a very high level of understanding, to me it feels like it's a snapshot approach, but with basically some optimizations around a few of the steps. One of those steps would be snapshot creation and maintenance, which I read from the dip that you wrote up. So for those of you who don't know what a snapshot is, could you briefly just re-say it in a sentence or two?
Yeah, sure. So when you have the blockchain state, right? So result of applying a lot of transactions. So you can time the state changes by blocks. So for example, we just say that at this block, there's this state, and then after another block, state changes. So the state transitions are like on like a block period. And a snapshot is pretty much just what the state would look like at a specific like block. So for example, let's say we currently mine like the tip of the blockchain is 1,500 blocks. So the snapshot is just state of that blockchain at like height 1,000, for example, or height like 100. You know, so it's just a historical state of the blockchain. That's all the snapshot really is.
Yep, and I think a good way for non-technical people to understand it is generally like at a like grocery store or a gas station. You'll have employees who basically check the cashier in the morning to see what the total dollar amount was when the day started, and then you'll have the cashier recount everything at nighttime, and then they'll have their nighttime balance and their morning balance. And basically, these are snapshots of the state of the money flow coming in and out. So
that's exactly right.
Yep. So with snapshots, I think you noticed that there were some issues around snapshots, like they may have been a little bit more bloated than they needed to. So one data structure that you kind of came up with was something, or maybe you came up with it, or maybe you were inspired by somebody else, but there's something called an ancestral record. Could you kind of speak on how that differs from a snapshot?
Yes. So ancestral records, great topic. Pretty much, okay, when you sync that state, right, when you have copy of the database, all right, I went a little bit too far. When you have the state, okay, and you are sending it, like another person is syncing from you, for example, you're sending it to that peer. Let's say you're running a node and I'm just sending you the state data. If I am currently processing blocks, that state can change. And then like, what do I do? Like, do I just send you new data? Like, what if like a lot of data was modified? Like, how do I know? Like, it's annoying to keep track of. So what people do instead is they just take the state, take the snapshot, right? So state at some like block height, take a copy of it, and then send you that copy, okay? Instead of sending you the actual production state that you're like adding new blocks to and, you know, processing and validating transactions. So ancestral records kind of like pretty much avoid copying the database. That's their main purpose. And every single blockchain was actually making copies. And that's so annoying. Like Ethereum, 300 gigabytes. If you really want to copy that data, like every week or something, or like, I don't know what's their snapshot periods, but like, if you really want to do that, that's like a lot of overhead. So what we do instead is like, between snapshots, we just record what changed. And that's much better because instead of storing like 300 gigabytes, you just store like maybe 2 gigabytes or 3 gigabytes, you know, like how much the blockchain can change in like 1,000 blocks, for example, you know, like not as much as in like 100,000 blocks. So which is like the whole like duration. So ancestral records is pretty much a way for us to transition between snapshots with minimal amount of data needed, and it's very, very important for scalability because we don't have to copy the database at any point. So, yeah.
Cool. And one thing that I thought was really cool about this that seems to be uniquely allowed on DeSo as opposed to chains that are more so Turing complete and don't have a fixed set of transactions is you basically use specific transactions to discriminate towards what should and should not be stored on this ancestral record. Could you kind of speak on the behalf of that also?
Yes. So, like in DeSo, there's like a couple of approaches of how you you can build a blockchain. You can like do like Ethereum, Solana, like the current movement in blockchain is like principle of generalization. So you want to like create a blockchain that can implement every single transaction. You can have like virtual machines, smart contracts, great, but when it comes to scalability, specialization is much better. Like Facebook is not an engine that can run Facebook and then like can run 100 of different platforms. It's just Facebook. That's like everything in their infrastructure is optimized for Facebook, right? So just like that, DeSo is optimized, okay, for specific use cases that we support, which is social media, social networks, and such. So in terms of ancestral records, the improvement is that pretty much the entire database is predetermined, like the schema for the database is defined, and we know exactly what records are in the database, and that just allows us to make a lot of improvements, such as we can sync from multiple peers at the same time very efficiently because we know how the data is divided, how there's a couple of things that I don't want to go into, but pretty much if you know how much data there is and like how much data you expect, you can make a few optimizations which make it faster. So that's one thing, and then obviously we can just handpick which data do we really want to sync, because some data doesn't really influence like how much money you have, for example, but like influence just some things that aren't really important and are just used for validation, for example, but you don't really want to sync it. So there's just a couple optimizations that we can do on that front.
Yep. So yeah, what I find cool about that is like very high level, it just sounds like you're able to trim the fat around what gets stored on here, and you don't even need to look at the data. You just look at the basically signature of the transaction, and you can immediately just toss it or keep it. And also, I'm pretty sure I read that you can later on asynchronously download the rest of the data if that's desired or something like that. So for any of the kiddos at home who are concerned about having a comprehensive state, that's baked into it too. But the optimization here is you get everything that you need first, and then you can download the additional fluff. Does that sound right?
Yes,
cool.
Exactly. So blocks is a very, very interesting example of that. So if you have the state, right, you don't really need these transactions. Like what these transactions are giving you, if you already know what data is a result of these transactions. The only reason you would need transaction is if like you have like some analytics where you want to like maybe see how like the blockchain, like how money moved throughout the blockchain or something like that. But like you don't really need like to have actually the like archive of everything that happened. You just care about the data. So when you hypersync, we like the whole idea was to move away from block syncing, like move away from the limitations of having to download every single transaction, and instead just care about the content of these transactions. So by default, you don't download the historical blocks before the snapshot. So, you like sync the state up to like certain point in history, and then you just disregard every block that was before that point. And that's like the default approach, and it just makes it much faster. But if you want to, you can turn on archival mode, which will then download all these blocks after you sync. So that is an option if you do want to keep the entire history of the blockchain, but that just is additional data that you don't really need. So
cool.
Yeah.
Options are always a good thing. And, some people will care a ton about making sure they have the whole entire, history of everything. And other people are like, I just want a production working node that can be spun up and start serving their application. All right. So
yeah, exactly. I can imagine, if I can just interject, I can imagine that some like people building like maybe machine learning on top of DeSo would want to see like how the like information propagates and all that stuff. So I can see that there's some applications to this. So you know, as you said, it's good to have options for sure.
Yep. I didn't even think about the AI part. That's actually a really cool idea.
Yeah, I mean, you can like trace where money moves, maybe like who posts what, or like, it's, you know, there's definitely some additional information in transactions that maybe you can utilize.
All right. So moving on to like kind of the next chunk of Hypersync. So we just talked about basically the ancestral records and the optimizations that they have over snapshots. And one additional optimization that you added, Piotr, was basically peer messages for requesting and sending snapshot data. So could you kind of speak on behalf of, well, first, what are peer messages?
Yeah, so the language might be like vague here, but it's like actually a very simple thing. So if you have nodes on the network, so you know your computer could be a node. It's literally just computer connected to the network and then connecting to certain IP addresses. Like as you're watching this video, you're connected to YouTube. You know, that's like you send a message to this IP address, and then it sends you a video, and you're watching me speaking right now. You know, so peer message in blockchains is just like the message, also network message that you send to other nodes in the network. So so that is all it means. It's very it's not as complicated as it sounds. It's just a network packet, and just send it to other nodes. And yeah, well, we just call them peer messages. And there's one for requesting the snapshot and then getting snapshot data. We have this pattern of when you request data and then the node responds to you with data, and that's the same for blocks or headers or anything else. The analogy is pretty similar to like just websites as well, right? Like you just send a request to get HTML of a website or like some whatever content, and then you get a response. So that's pretty much similar. Yeah.
Would you say it's kind of similar to like how the HTTP protocol kind of works?
Exactly.
Where it's a request to a server and then it responds to the client?
Yeah. The only difference is we use like TCP because it's just better for our case. But yeah, it's the same like principle. Okay,
awesome. And if anyone out there is kind of curious on what these peer messages are, Piotr wrote a DIP on basically everything Hypersync is, and it goes into all the technical details, and it includes a reference to all the peer messages. So if anyone's interested, I'll include a link wherever this video is supplied to, and you can check it out on your own. All right. So awesome. now that we know what peer messages are, could you speak about what multi-peer sync is? And this is something that I thought was just so cool.
Yeah. So have you ever? Okay, I don't know if this is a legal question to ask, but have you ever used BitTorrent?
Yes. I was.
Okay. Hypothetically, allegedly, maybe not even allegedly, just hypothetically. You know, just you know how it works, right?
Yep.
So you have like seeders, I think that's what it's called, right? And then like you know, like download the data. So and like what BitTorrent does is like you just download the data from multiple people at the same time, and it just splits like I don't remember how exactly the protocol works, like how they call it and all that stuff. But you split the like a movie or something into like smaller pieces, and then just sync from multiple people at the same time, and that's just better for like bandwidth, and you can just download the data faster. So we do the same thing in Hypersync.
All right. So now we kind of covered the optimizations that have been made around a snapshot and trimming the fat around them and making them into essentially an ancestral record to improve downloading times. The next part of Hypersync that I thought was pretty cool was multi-peer sync. But before we go into multi-peer sync, could you first explain what a peer message is?
Yes. So peer messages, I know that this might be like a vague term, like what does it even mean? What even is a peer, you know? Like, and then messages, okay, messages may be less complex, but peer is like another node that is running the DeSo blockchain, or any blockchain, to be honest. So if you just spin up a node on your computer. Just go into the code, download it, run the Docker image. You now are a peer to someone. A peer is just another node that is running the DeSo blockchain. So peer messages is just a name for the communication, the network communication that you exchange between different nodes on the blockchain network. And this includes, in terms of the hypersync, you ask for the state. So you send a get snapshot request, and then the peer responds to you with a snapshot data request. So these are just messages that we just custom made, and we just call them this way because like the nodes know how to interpret these messages. And they're like, it's very similar to like how you like access a website. You ask for a website and the website gives you the content. So it's the same, but with just happening on a blockchain. So the messages are a little bit more optimized and all that.
Mm-hmm. So basically it's one node signaling to another node that, hey, can you do this for me over here? Or, hey, node, I'm going to start doing this over here, just to let you know. Does that sound correct to you?
Exactly, yes. And these are just network packets. So it's like a specific network message that you send over TCP if you want to be super precise. But that's all there is to it.
Yes, the precision is always appreciated. So that leads me into the next optimization on Hypersync is what is multi-peer sync?
Oh, that's a great topic. So when you sync, that's like we're going like a step beyond just Hypersync, and I just want to make it even faster. So you can like when you download this this snapshot, right, the state, you could download it from just a single node on the network. Just let's say I'm just asking your node, Ty's node, like, hey, what's the snapshot right now? And you just keep sending me data. That's fine, but like, it takes you some time to fetch this data. It takes some time to go over the network, What if you could just ask like 10 people at the same time, like for the data and just download it like all at once instead of just asking one person? So multi-peer sync is exactly that. You just, because we have a strictly defined database schema, we are able to know how much like data to expect at a certain like bucket, which we call like prefixes, but we just have like a little bit more information about the structure of the database, so we can efficiently sync from multiple people at the same time, and it's just much faster. So that's what it is.
Sweet. Yeah, and one thing that I thought was cool was multi-peer sync does make use of basically the state data prefixes to have a little bit of an optimization around these download times. I know other chains can also do multi-peer sync, but from what it sounds like, DeSo, because there are prefixes to the state, they can do it even quicker.
Yes, exactly. Because we don't have like smart contracts, for example, we know it takes us much less effort to know how much data a certain like database record is supposed to have, and then how to like delegate it to the peer, like which one to ask. It's just much more efficient on DeSo. So because we have a strictly defined database schema.
Yep. Cool. All righty. So I was reading your dip, and you basically talked about some of the caveats to multi-peer sync, and some of these issues seem to be that there might be peer downtime, there might be network drops, and you might just be talking to a slow node. And my initial thought is like, oh yeah, if you're talking to like 10 different nodes, like at the same time, and 2 of them are acting bad, like could that get messy? Or did you kind of add some solutions in place to handle these issues?
Yes. So because what we call the actual like the network is like asynchronous network. That's like the terminology for what the blockchain network is supposed to be. And what it means is that like you don't really know like how long it will take another person to respond to your request. You don't really know like if they ever respond, like because you don't really, it's all like trustless, right? Like you could like just turn your computer off at any time and I don't really know what's happening. So so there are all these things happening, and we just implemented some mechanisms that allow you to identify if a certain node is just like sending data too slowly. Another like peer can take over a prefix, for example, or can just like speed up the process. And Because, if you were like confined to just one peer that you're syncing from, and then they're like super slow and they send you like megabyte per second, speed. It's so funny.
Mm-hmm.
Like 10 years ago, that would be like insane speed, right? But now like it's so slow. Then like you would just, ditch them and then switch to another peer. And that's pretty much what you were referring to.
Yep. So basically, Hypersync is self-reflective, where it kind of has a level of quality control to it, and it will kick off nodes that are not cooperating as expected, or
Exactly.
as expected.
Yeah, there's also another cool thing. It's good that you mentioned that it has like quality control. Another thing that I've added is a recovery mode. So if you're a developer and you're running a node, you might have seen these around. So pretty much if you like shut down the node unexpectedly, the node is able to recover. So it is able to like figure out what like went wrong when it shut down unexpectedly, like the power turned off or something, and it's able to like revert to a state where it was stable and then just keep going on from that point. So that's another like cool little detail that we've added with this change.
It's a snapshot to the snapshot.
Oh yeah. Oh dude. Yeah.
Alrighty. So multi-peer sync, by the way, when I first read that, I just thought that was awesome. But on top of multi-peer sync, there's an additional benefit to Hypersync, which is elliptic sum. And this one is, yes, this one was definitely the most technical, and I felt like I was in my college class again, like reading white papers and trying to like write a proof or something. And
here we are.
If you want to read,
I'm in college, so
yeah, so it's fresh. It's fresh. And again, if you want to read about any of this, I'll be sharing a link to the dip that we have that goes over Hypersync, so you can read all about the white paper that Piotr was inspired by. But basically, from my understanding, elliptic sum is replacing the checksum solution that traditional blockchains have in place, where they use a Merkle tree and they basically do the magic that blockchain does, and they get a verifiable node or something like that to verify that the data being sent over is legitimate and it's not something being modified by a malicious node. So one of the downfalls to the Merkle tree approach, from my understanding, is it takes up a lot of data. So could you speak on behalf of elliptic sum and like basically why haven't people been using it before, and then what are the benefits to it?
Yes, so I think I'd start with why haven't people been using that before? I think in crypto, what happens a lot of times is that like protocols just copy from one another, and sometimes they don't really like try to like iterate on this and make it better. So for example, Solana tried to do this, and then they kind of like didn't do it properly, and then they just reverted to Merkle tree. So there's been a movement started to replace Merkle trees, and I think elliptic sum is that replacement. We have to peer review it a little bit more just to make 100% sure, but I'm confident in the theory. So pretty much what's like the problem with Merkle trees, and why do we even need this thing, and like what it's doing? Why does it have its own name? If it has its own name, means probably it's important, right? So let's talk about that. So you mentioned like validating the state, and that is a very important thing. It's like the most important thing in state sync, because when you are like downloading the data, you're in a trustless environment, meaning that you don't really know that you're receiving like the correct data, and that the node isn't like a malicious hacker that is trying to fake that they have like $1 billion or something. And you need to have a way where you can like make sure that the database cannot be tampered with. And when you state sync, it's even more important because you don't have like a blockchain that like supports the stake sync, because you don't download the blockchain, you only download the state. So what you do is you imagine just take a hash of the entire database, okay? And this hash, now, if you get this hash, get the database that you've received from your peers, and then you hash this database, you should arrive at the same hash that was initially, computed when you were like producing the state. And then to make it secure, you actually put this hash which is called the state checksum in, for example, headers. And then it's like verified by proof of work and all that stuff. Might getting a little bit too complicated here, but pretty much if you have a hash of the state, then you can prevent peers from tampering with the state. And what people, does everything make sense so far?
One cut in for the non-technical folks out there. Basically, the hash, I would say that's similar to the outcome of solving, let's say, your algebra math problem, where you have like 2x plus y times 20.
Great analogy.
Everybody has access to that math equation when you're taking a test, but the hash would be the actual answer to that equation. And you can basically verify that the answer is correct by having a node basically run the equation itself. Yep. So,
exactly.
So just for the non-technical folks at home, that's basically what's happening there. So you can continue where you left off.
Yeah, if I can expand on this analogy, I really like this. So imagine if instead of having X and Y, you have like X, Y, Z, and then you keep going and there's like a million of variables, you know? So that is a pretty big equation to solve, you know? Like your methods of like the Gaussian elimination or whatever you're doing there of like solving these equations is like pretty bad. But so you can't really like fake solution. You have to really like know the solution to make sure that the equation is correct. But how do you like confirm that the solution is correct? So you take the hash of all the values, and then that's like maintaining integrity. And then if I give you the variable values and then I give you the hash, then you can confirm that you have the correct variable values, for example. Anyway, that was like more in-depth analogy maybe to the state checksum. Maybe that made sense, hopefully. So
no, I thought it was great.
Yeah, so but continuing. So you have this hash that represents the entire database, and there's just a little bit of problems. Let's say you just do a straightforward hash of the database. Now let's say you want to modify a single record. What happens to the hash? It's different now, right? Because you just changed the single thing in that entire database. But because we're just taking hash of the database, you'd have to go for the entire data and rehash it, which is terrible. That would like be extremely slow. Like imagine just rehashing 300 gigabytes every single transaction you make. It's unacceptable. So so what you do is you build Merkle trees. So Merkle trees is a very smart structure where not going into too much details, but updating a record doesn't require you to recompute hash of the entire database, but requires you to recompute like, let's say like 20 hashes of like small chunks of data. So that's pretty much like what Merkle's break down the problem. You know, they simplify the problem of recomputing the hash of the entire state to just recomputing like 20 hashes of like small pieces of data. The problem is that there's a lot of these small pieces of data. And if you have 300 gigabytes of state, that can be like 30, 60 gigabytes of data of just additional like these like pieces of data that you need to keep around. And you have to store them in the memory, unfortunately. Otherwise, you have to do like very weird, like random access, like just guessing. Like it's tough. If you don't store it in memory, it's just the IO operation is just going to like kill you. So so that's what people do in Merkle trees. And the problem is that like let's say instead of 300 gigabytes of state, now you grow to like terabyte of state. Now the size of this Merkle tree increases. So now instead of being like 64 gigabytes, it's like or like whatever, it's like 128 gigabytes or like even more, you know, and then like it keeps growing of the size of the database, and it's a pretty like significant size. So so we have to get rid of it, okay, and we have to solve the same problem, hashing the entire state, but without this additional data that is just useless to us. So elliptic sum is exactly that, and instead of storing 64 gigabytes of data, guess how much data you store? You do the same thing.
I don't know this one. I'm going to guess 20 gigabytes. I could be completely wrong though.
33 bytes.
33 bytes, folks.
Oh yeah. Whew. Yeah, that's quite an improvement, eh?
Yeah, that's actually insane. That is so insane.
Yeah, so you don't have any additional storage, And to do this, you're solving a totally different problem. You're not doing like Merkle trees or anything like that. You are hashing, but you're hashing to a very specific algebraic group. I'm just going to make it vague and give it a that.
And just to clarify, this is
yeah.
elliptic sum that you're talking about, correct?
Yes, this is now elliptic sum, yes. So instead of hashing, like if you take a hash, it's just like a number, right? It's an integer. But in elliptic sum, you don't hash to like integers. Like hash is just a very big number. It's just 2 to like 256 minus 1 number, like pretty much. So elliptic sum is not hashing to integers, it's hashing to elliptic curve points. So, and then because of the hashes are on elliptic curve points, you can like add them together, which you couldn't do with integer hashes, and they still maintain a couple cool properties. So I know we're going very theoretical here, but pretty much you can just get away with 33 bytes instead of 60 gigabytes or whatnot, you know, so it's a little bit better.
Yeah, no, that's honestly, that number is bigger than I thought it was by,
or smaller
by
than
like a magnitude, or smaller. Yes, you are correct. Yes. I'm conditioned to think bigger is better, I suppose. But anyways, so essentially elliptic sum, it on a very high level, instead of storing all these hashes, which are these very large numbers, they store these points on a elliptic curve instead, which
just
intrinsically hold just 1 point, which intrinsically holds the information in a smaller, more compressed version than the integer hash.
So in the Merkle tree, you only really care about one single hash. And it's a tree. So if you Google Merkle tree right now, you'll see a nice tree, and it's like kind of like a pyramid, all right. And the very tip of this pyramid, is that how we pronounce that word? Pyramid is the root hash. So the very top hash is called the root hash, and this is honestly the only piece of information that you care about. So all this 60 gigabytes of data just for this one hash. But in elliptic sum, you don't need this additional data. You just store this single hash. So that's like the difference, and we can accomplish this because cryptography, you know.
Awesome. And if you're wondering more about Cuz cryptography, again, check out the dip that Piotr wrote up. It has references to all the papers that he drew inspiration from. Anyways, I personally feel like we covered the main points of Hypersync pretty well. Was there anything that I missed that you wanted to talk about?
I think that was great. I hope, you know, people enjoy this. I hope like I made sense. I mean, like I was like too theoretical. I guess like the only additional like thing that I would say is that Hypersync is not just the sync itself, but we've actually added a lot of like other cool features to the blockchain. Like it's like a general like improvements to the core repository, I'd say. And this like includes like one cool thing that we've added is encoder migration. So this is just like the technical like appendixes for people who got to this part of the video and just want to hear like a little bit more. So encoder migrations are pretty cool. You can change the schema of the database without requiring a resync. So that is very important. You can change existing records in the database, the schema of these records, and you don't have to resync from scratch. So that is pretty good. Like I can't stress enough like how good this is, because you can like make changes and like they're super seamless, and you can upgrade the network like pretty much however you want now when you have the schema changes. And then we added like
You're saying a schema change no longer means downtime for a node.
Yes, exactly. So for example, what it exactly means is like, let's say that now when you make a post, you want to like, I don't know, like add a picture to this post, but now it's like an additional field or something. I don't know, like maybe let's find a better example. Like you want to follow someone with a diamond, okay? You want to like follow someone and send them money. You can like change the transaction, not the transaction, but you can change the database records that are like related to follows, and then the database is not going to break, and you can just like augment the database at any time, and it's like there's no downtime, as you said. So that's one thing. And then
well, I was just going to say that's pretty crazy, and I didn't even know about that part either. So I'm learning as we go here.
Yeah, these are like little hidden things that we've added. It's actually interesting. So there was a problem that we found. Theoretically, if you were like hypersyncing and you were trying to, or state syncing, and you were trying to upgrade the protocol, the problem was like which node upgrades first. Like you don't really know like which one is the source of truth, because if you change the database schema and like you send the snapshot, now the data that you send in the snapshot is different. So like if you upgrade, like which node has to upgrade first, like it would have been tricky. So encoder migrations was like a solution to this, and then we also used it to just get a little bit more generalized. I guess this is more like, we could probably simplify this point, not include everything in the video, but yeah, so that's one thing. And then another thing, yeah. Any questions to that, or should we move to the next thing?
No, I think I've got at least a high level understanding of it. If any more meaningful questions would have to come from me reading a little bit more on it in my free time.
Yeah, I have another interesting change that we've added, adding to this like appendixes of changes, is integration tests, which are pretty much we had the unit test, which is like, let's test this one module of the entire core repository, like just this one functionality, and like let's just see if it works. And integration tests are, I give you a node, or like I give you a network of nodes, like 5 different nodes, and I connect them in a very specific way. And then at the end, once all of them sync, I want to like make sure that they have the same data in their databases. And now it's like, it's a testing framework. So we can use it to like test proof of stake. We can use it to like test all the other like cool protocol changes like sharding and all that stuff. And it just speeds up development even further. So that's like another cool framework change that I made. So yeah, that's, I guess, like another feature.
That's great to hear. So basically, making more changes to DeSo in the future will essentially be easier because we have more foundations in place to basically automate a lot of the annoyance manual changes that people had to traditionally deal with prior to.
Exactly, when developing the core repository. So as I said, it's like a general like protocol upgrade, I'd say. So a set of cool features, new features have been added. So yeah.
Awesome. So any other little gems tucked away in Hypersync?
I think this is all from me. You can always look at the repository and look at the pull request and the commit now, and just, go through it. It is a little bit of code, like 14,000, I think 14,000 lines of code. So it might take a little bit of time. But, if you do understand it, I mean, I'm always happy to answer any questions about the code. So, but go into the DeSo protocol core repository on GitHub, and we can check it out on your own too.
All right, Piotr. Well, I gotta say, I am blown away with Hypersync. I was blown away when I first heard about it. I was blown away when I was reading your write-up on it, and I'm more blown away again after getting a little more of an in-depth conversation about it. Last question for you. So yes. With Hypersync,
also thank you very much, by the way. Just
absolutely.
That's a very nice comment, Ty. Thanks.
No problem, bud. So with Hypersync being out and available for our nodes to use, how do you think this will impact DeSo in the short term and long term?
Yes. So in the short term, obviously you're going to sync in 20 minutes compared to 8 hours. So that's pretty good, I'd say. I guess that's also long term. But the more data we add, the sync time is going to increase. But we could probably cut it down to my best estimates to like 5 minutes if we get like really, really good. So, but that would require like sharding. So I think we can do that, but we just have to get like a little bit smarter. But better sync time, short term, long term, the entry to barrier for new validators. Once we move to like proof of stake, for example, especially then, it will be just like very small. Like you can just spin up a node in 20 minutes and then you can just join the network, and that promotes decentralization. Better censorship resistance. The more nodes you have, the more copies of the state. So a lot of changes, and the lower the barrier to entry, sync time is one of them. The better we can do in terms of these properties of our blockchain. So that's definitely the two most important things. spinning up a node quicker, better development. You can test things quicker too. So that definitely helps.
So faster sync times and a much user-friendly, faster node syncing operation, pretty much, to make the lives of developers and node operators alike have a much better time building on the DeSo chain, or improving upon, I should say.
Exactly.
Or
they can deploy their own social network if they want to, and just take 20 minutes,
Yeah, no big deal. Just deploy their own social network.
Probably nothing.
Alrighty, Piotr. Well, once again, thanks for taking the time. I know you've got a very hectic week with everything going on. During exam week, if that wasn't mentioned already.
This is my finals week. So unfortunately, I have a lot of work, non-technical work, unfortunately. But we're gonna get through it. Just two more to go, so I think I'm gonna do fine. But yeah, thank you. These were very insightful questions. I hope that people learned something from this video and like it. And we can maybe continue in this format. I had a lot of fun recording this, so that was it's cool. Yeah.
Sweet. All right, guys. Thanks so much for watching. Until next time.